Today's lesson is on work, energy, and power. Work is the energy that's transferred when a force is applied to moving distance. Work is force times distance. If you remember, we learned about that earlier this year, so this should be a review. Work is only done by the force that's parallel and in the same direction as the distance. And the units of work are in the metric system are joules, and 1 joule is equal to 1 Newton times a meter. And if you take in chemistry class, you probably have also used joules as a unit of energy, of chemical energy. It's the same unit. Here's an example. A student is lifting a 50-pound ball, 4 feet. How many joules of work were done? Again, work is a force times a distance. So the force is 50 pounds, okay, and the distance is 4 feet, so it's 200 foot times pounds. This is work, but this is not joules. Okay, if we want to convert it to metric units, SI is metric units, 50 pounds, okay, the conversion, and you can find the conversion on the formula sheet, is 1 Newton is equal to 0.225 pounds, so we get the 50 pounds of force is equal to 225 newtons. 4 feet, and the conversion between 1 meters and feet is 1 meter is 3.28 feet. Again, this conversion factor you can find on the formula sheet. 4 divided by 3.28 gives you 1.22 meters. So then work is force times the distance, which is 222.5 times 1.22 meters, okay, which will give us 271 joules. Energy is defined as the ability to do work. You've learned in middle school as well as high school about different forms of energy, and we use energy all day long. Okay, light is a form of energy, heat is a form of energy, mechanical systems are a form of energy, chemical energy is a form of energy, such as, let's say, like batteries, or when you combine chemicals together they sometimes produce heat. There's also electrical energy. Okay, these are all forms of energy, and energy can be converted between any of these. A roller coaster is an example of gravitational energy. Solar sail is obviously using sun, and fuel cells are essentially similar to batteries. We're using chemical energy. You learned in middle school about potential energy. Okay, potential energy is also known as stored energy. It could be gravitational, or it could also be chemical. I guess the capacity to do work by position, by lifting something up by some kind of configuration. So you're using gravity, in this case, to do your work. Kinetic energy, again, you learned in middle school, is energy of motion or energy of movement. For example, you've got water here in this dam here. When the water moves through a turbine, it directs a turbine to produce energy, which produces electrical energy. These are examples of wind turbines, what people call windmills, that produce electrical energy. Another example of energy of motion is this rocket here taking off. Energy can be transformed from different types. So, for example, when we eat, we take chemical energy and we convert it to kinetic energy when we're able to move. The radiant energy of the sun we can use to store inside chemical energy, and we can use electrical energy, such as in power lines, the electricity that comes into the house, to convert it to thermal energy inside, let's say, your oven. You've learned about renewable energy sources. You've learned about biomass, or living things such as corn, sugar, etc., hydroelectric power, geothermal, wind, okay, as well as solar. These are all renewable energy sources. Non-renewables you learned about include coal, natural gas, petroleum, which is oil, as well as uranium, which is nuclear energy. The law of conservation energy says that energy cannot be created or destroyed, but it can be converted from one type to another. But anytime we do conversions, though, we always lose some energy. We always lose some due to friction. So that some energy is always lost to heat. When input is converted to output, we always lose some. There's never 100% efficiency. Some examples of converting energy is when we're using an internal combustion engine in our car. We're converting chemical energy to heat, which converts to mechanical energy, which is what makes your car move, as well as electrical energy, which also helps to run the engine, also runs the radio and lights in your car. Solar cells are where we're converting sunlight to electrical energy. Wind turbines convert kinetic energy of the wind turbine to mechanical as well as electrical energy. Hydroelectric plants convert the gravitational potential energy of water to mechanical and then to electrical energy. Nuclear plants, like the one in Indian Point in Westchester, convert nuclear to heat and mechanical and then ultimately to electrical energy, which powers some of our electricity here in Rockland. Vehicles such as combustion gasoline or diesel vehicles convert chemical energy to both mechanical energy as well as heat. The goal in a car is both mechanical and heat energy, right? In the summer, we need the mechanical energy. In the winter, we need heat to warm us up, keep us warm inside the car. Efficiency, we learned a little bit about efficiency a couple months ago. Efficiency, for efficiency, we use this Greek letter, we pronounce it eta. It looks like a little z, little script z. Eta represents the percentage of input energy transformed to output energy, or E out, energy out, okay, divided by energy in, okay, times 100%. Again, this formula is in your formula sheet, so you don't need to memorize it. So we always write it as a percentage, and we would always expect that our efficiency is always going to be less than 100% because we're always going to lose a little bit of energy. Current energy concerns, as you learned about a few months ago, is pollution, depletion of non-renewable sources. Dependence on energy can cause problems if we're dependent on other countries, and now all of a sudden there's, let's say, an embargo or there's a war. And also cost of energy can also be a concern. This is an example, or this is a diagram showing our consumption of energy by source. Our largest source tends to be petroleum, which is non-renewable, then natural gas, which is also non-renewable. After that is coal, which is also non-renewable, and some of the smaller ones include uranium and propane, which are all non-renewable. And these renewable ones are all very, very small percentage, although biomass tends to be increasing. Biomass is, for example, if you've got a wood stove at home. Geothermal, wind, as well as solar are renewables that are very small percentage, but also increasing, and we expect those to be increasing in the coming years. Certainly, the incoming federal administration we expect is going to increase these renewables because of the role of all non-renewables in climate change. What roles do engineers have in energy? Engineers obviously have a significant role in all those forms of energy. Power is the amount of energy that's used up per unit time. Remember, energy we measure in terms of work, so power can also be written as work divided by time. So the units of energy, we said, are joules. Okay, the units of work are joules. Time, unit of time is seconds, so the unit of power is 1 joule per second, 1 joule per second. Well, we learned when we were learning about electrical circuits that we measure power in terms of watts. 1 watt is equal to a joule per second. So when you are measuring watts, you can convert 1 watt to 1 joule per second. We've learned a little bit about electrical power. We did that in the last couple weeks in terms of electrical energy, where you're converting energy using electrical energy to produce work. Mechanical power uses mechanical energy. You learned about that when we converted force times the distance. We calculated work. That could be linear mechanical motion or rotary motion. We will be learning later this year more about fluid power, where you're using energy that's transferred by liquids. That's what we call hydraulics. Okay, and when energy is used by gas, which is called pneumatic. Here's an example where we're asked to calculate power. Well, somebody is lifting a 50-pound ball 4 feet in 5 seconds. How many watts of power? Well, first we need to figure out the amount of work. Well, we already did that conversion before, right? We converted it to metric, and we got 271 joules. Okay. Well, power is equal to work divided by time. So the amount of work we calculate is 271 joules. Well, we're given that it was over 5 seconds, so 271 joules divided by 5 seconds. 271 divided by 5 gives us 54.3 joules per second, or that could also be written as 54.3 watts. Again, this formula, power equals work over time, is in your formula sheet. You don't need to memorize it.